Okay, I'm going to get started. I think Cedo is going to be here in a second, but he can join when he's here.
I'm here.
Cedo, you're here. Great. Okay.
For 5 minutes, then I'll keep it open. So I will be back in 10.
We've got Cedo here for 5 minutes. Basically, what I wanted to do was to set up a breakout room for anyone. So we emailed around some steps that we wanted you to do before the workshop. And the reason was because we're going to be using simulated data, and there's some steps for you to be able to access that. So if you haven't been able to, let's stop sharing this for now. If you haven't been able to follow these steps, or you've had any problems, I'm just going to make a breakout room now. Could you move yourself into the breakout room, and Cedo will try to help you solve these problems in the 5 minutes that he has before he has to jump off. I'm not sure how easy it is to move yourself to a breakout room.
Where is it?
Can you see it?
I'm not seeing it, Tim. Are they? Oh, right. You just, yeah. It's just popped up for me. I don't know if for anyone else.
Okay, cool. So I think you just have to accept the invitation if you need to go and join that room. This is for anyone that hasn't been able to follow the steps and wants just a bit of help from Cedo. Okay, great. I'm going to get going while Cedo tries to help some people with that. Let me make this big. Okay. First, I just want to start by thanking lots of people who have helped prepare this tutorial. Lots of people are on the call now and are going to help throughout the tutorial today. Rachel Hughes at Bristol actually generated all the data we're going to use, and then Cedo, Dimitri, Alex, many other people have helped put this together. So what are we going to do? I've put 5 minutes on technical issues. We're up to 10 minutes on that, but Cedo hopefully will sort people out with their difficulties. I'm going to give a brief introduction to mixed effects multi-level models. These are the statistical models that we'll use to model trajectories. I'm only going to spend 10 or 15 minutes on this, and this is going to be a super brief introduction. I think you could spend 2 hours talking about this at least, but I really want to get on to the practicalities of doing these sorts of analyses in Datashield. So we'll have a little introduction to what we're going to be doing, and then we'll have the first practical, which is how to visualize repeated measures data in Datashield, and then how to fit some simple mixed effect trajectory models. Then we can have a little break, and then we're going to move on to some more complex models, so trying to model nonlinear trajectories. I think Cedo and Andrew are around to help with some technical and Datashield issues. I'm not a statistician, so I've asked Dimitri and Daniela if they can chip in if any people have got any more difficult stats questions. Alex is going to help by monitoring the chat and pointing out if I miss any questions. So there's a lot of interchangeable terminology for these types of models: mixed effects models, multi-level models, trajectory models. I'm treating them all as basically meaning the same thing. Some people call mixed effects models, other people call multi-level models. It's all the same. And I don't expect everybody to take everything in from this tutorial, but I think what I want to do is have a nice document that people can work through when you come to do your own analyses. We're going to leave the simulated data online. We will probably host this, the R script maybe on Datashield website or somewhere where you can easily access it again. And it should give you the steps when you come to do your own analyses. So I've said here that there were some pre-workshop steps. Any problems, to move yourself into Cedo's room and he should be able to sort you out. Alternatively, if you don't actually want to do the analysis yourself, but you just want to watch, that's absolutely fine. I'll share my screen when we get to it and work through the analysis. You can just see it. Okay, well, I guess the first question is why should we model trajectories? And we've got amazing data now. I mean, Lifecycle has been an amazing project, harmonizing all of this data across cohorts. We've now got this amazing repeated measures data up to 18. And to fully understand the course of disease, we need to look across the lifespan. So these models can help us not just get a snapshot of health, but see how health changes across the life course. So I've just given a few example questions here that that you might need. Sorry, did
Tim,
someone?
we cannot see your presentation.
Ah, can you see it? Nothing at all?
No, can you share again your screen?
Yeah, I can. Thanks, Dimitri. Can you see it now?
Yeah.
Okay, let me make it big. I think I may have forgotten to press the screen share button. So yeah, I was talking about why we model trajectories. So we can understand health across the lifespan. So I've given some example questions here of how do socioeconomic inequalities in health change or emerge as children age? Which factors are associated with cognitive decline? How does exposure to environmental pollutants affect children's cognitive development? For all of these sorts of questions, we might want to use repeated measures data and look at change in our outcome. So conceptually, how do we model trajectories? I think to understand mixed effects models and multi-level models, we need to start by understanding the normal linear regression. And this should probably be clear to most people here because it's sort of the bread and butter of the sort of association analyses that we do in epidemiology. So with linear regression, we're modeling the relationship between an outcome and one or more predictor variables. I've just put the very, very simple linear regression equation down here. So for each individual I, we're estimating the value of the outcome as a constant, an intercept, plus a slope multiplied by the predictor variable, plus an error, because our model isn't going to be perfect. Now, one question is whether we could just use linear regression to model trajectories. Well, you could do, but it's likely that the estimates you get aren't going to be precise and they may be biased. So one of the assumptions of linear regression is that the error terms are not correlated. But if one individual's providing multiple observations, this is not likely to hold. So linear regression assumptions may hold if you have one observation from each individual. But imagine that we've got a data set where each individual's providing 5 or 10 observations. If I'm significantly over the average weight at age 5, I'm also likely to be over the average weight at age 10 and age 15. So the difference between my observed and predicted weights are likely to be correlated. So you're going to have these patterns of correlation in the data. And one of the key assumptions of linear regression won't hold. Just got a couple of things in the chat. Okay, thanks. Pointing out that we couldn't see the slides. So this is where mixed effects models come in. So we overcome this limitation by including information about clustering in our models. So whereas a linear regression, you'll have your outcome and then you'll have a number of predictors. With mixed effects models, you've got another bit of the model. And this is where you provide information about the clustering in your data. And this is what we call the random effects part of the model. And I think from a modeling analysis perspective, this is probably the main thing to take away and have in mind, that actually we're not doing anything which is hugely more complicated than linear regression, which everyone will be familiar with. We're just going to specify another part of the model, which is saying how we think the data is going to be clustered. Below, we've got an example of a simple cluster structure for longitudinal data. The level 1, which is where the observations are. So this is each data point. And then we can specify that these observations are clustered within individuals. So individual 1 might have 4 observations, Individual 2 might have 2 observations. Individual 3 might have 3 observations. So we can describe the clustering we think is in the data, and we can include this clustering as information as part of our model. And I'm going to give you my very layman's non-statistical understanding of mixed effects models, but essentially they work by fitting separate lines for each cluster. So in the example of repeated measures data, we're saying that each individual constitutes a separate cluster. And we're going to fit a separate line for each individual. So you've got the, try and unpack what you've got here on the right. So the beta 0 would be your average line, your average intercept for the whole sample. But you also are predicting these separate lines, the top dotted line and the top bottom dotted line. This would be an example if you only had 2 subjects in your study. So you're predicting a separate line for each individual, as well as the mean line for the whole sample. And the simplest mixed effects model for repeated measures data that we can fit is called a random intercept model. So in a random intercept model, we estimate the mean intercept and slope for the whole sample, the average intercept and the average slope. And this is what we mean by the fixed effects. But we also estimate another parameter, u. And this is a parameter we estimate for each individual. And there's a difference between each individual's intercept and the mean intercept of the sample. So we get information not only about the average slope and the average intercept for the sample, we get information about how each individual differs from this average. And this is the random effects, which is providing this information about the individual difference from the average. Now, the overall random effects have a mean of 0, but the standard deviation gives you information about the level of variation. So if you have an intercept of 20 and then a standard deviation of 30, you've got a situation where you've got a huge amount of variability between individuals. If you have a very small standard deviation of the random effects, actually you're saying that each individual within your model is quite similar. Now that might be the briefest introduction to mixed effects models that you're ever going to get. And I kind of want to just leave 5 minutes for people to ask any questions or give me some indication whether that's very familiar and makes sense, whether this is completely unfamiliar and people are completely lost. If people want us to spend more time going over mixed effects, we can do. Or if people want to get more into the practicalities of doing the actual modeling, then we can move on to do the modeling now. So some sort of wave or something in the chat, or if someone wants to sort of let me know where you're left with, then we can decide how quickly to press on. Should we do a poll? Yeah, that's a really good idea. How are we going to do a poll, Serena? Is there some sort of
Sorry.
hand put?
Yeah, there is some. I'm not familiar with the tools, but there is some online tools. You can just share the poll and we can say familiar, not familiar, and then we will have a better, because otherwise we are 37.
Yeah. Is there some sort of hand thingy that you can do in Zoom? I'm not super good. Can you put a hand up?
Down at the bottom of your screen, you should have reactions, and there's a green tick and a red cross, and I think the host can see the numbers if you tick or cross.
Okay, nice. Could people say a tick if they feel like they're kind of got good enough understanding to press on, or a cross if they're completely confused?
Also, Tim, I'm no longer a host at all. So if you could give me co-host, then I'll be able to see the results.
Sure. I'm going to have to just stop sharing briefly to do that.
Where is
Oh.
that?
Okay, I can see some reactions on the right hand side.
Yeah, we're getting lots of ticks.
Oh yeah, here we go.
Good. Okay, more ticks than reds, or the red people are shy. Okay, nice. I don't know how to make you a co-host.
You right click on my name.
There we go.
Yeah.
Okay,
Thanks.
great. I'm gonna push on so we can actually get into Datashield then, because it seems like the general principles are clear. And I think even if they're not super clear, we can show how to do the modeling in Datashield, and these are things that you can come back to, you can look up in your own time. In fact, let me just share my screen again. Put some references here in these slides. And again, maybe I could ask Marika to circulate these slides once people are done. Can you see them again? So there's a paper that was written by Rachel Hughes, Kate and Deborah from Bristol, which is all about combining longitudinal data from different cohorts, which has just been published in the last month or so. So this is a really nice sort of conceptual paper about combining trajectories across cohorts. This is a great paper by Kate Tilling and lots of other people from Bristol, and it's a really nice step-by-step example of how to model childhood growth using different multi-level model methods. And at the bottom here, there's another great course, which is by the Centre for Multi-Level Modelling, also at Bristol, so I'm biased. But I think it's a free course and it will take you step by step. So these are not Datashield specific, but in terms of understanding multi-level modeling and doing it in R, these are great resources. Okay, let me get my R up. Okay, so I'm hoping that you can all see RStudio opened up here on the top left.
Yes.
Thank you. So we've got a simulated data from 4 cohorts, Ausbach, BCG, Born in Bradford and Probit. So none of this is real data, it's all simulated. And this is held on a server, which we're all going to be able to log in and access the data. And the aims of the analysis today are, we're going to model child weight trajectories over time for these 4 cohorts. We're also going to model sex differences in weight trajectories. And we're going to show how to combine these trajectories by 2-stage meta-analysis, so we get a overall combined trajectory for the 4 cohorts. We're going to work through describing and visualizing the data, fitting simple models, and then getting on to fitting some more complicated models. I think I'm going to try and err on the side of going through this slowly, so we might not finish. But I think it's better to understand, especially the first couple of stages and the first simple models, and then it should be easier to get onto the more advanced ones. But we'll see how we get on. Maybe we'll get through the whole thing. So the first stage, which I'm hoping either everybody has finished this stage, which is to install some packages, or they've had a word with CEDO and they've managed to get access to the analysis server, whereby you can do the analysis all remotely. So if everybody could get, either if they want to do the analysis themselves, get up their own RStudio, or if you just want to watch the analysis, watch me do it, I can talk you through as we go. I'm just going to give you a couple of minutes just for everybody to be set up with their own version of R. So first of all, we're going to load some libraries. So these are just a number of libraries in R. So there's some R, but normal R libraries, and then there's some Datashield based libraries that we're going to need to do the analysis. Now I use a lot of tidyverse syntax, a lot of tidyverse packages in R. They may not be familiar to other people, but I think they're super nice cluster of packages. So if you've got any queries, then let me know, and I can try and explain exactly what the syntax is doing here. Sido's back. Hi, Sido.
Hi.
Kids picked up?
The kids picked up, yes.
The first thing we need to do is we need to log on to the test server. So this is a remote server operated and manned by Sido, which is going to hold the data for the simulated data for the 4 cohorts that we're going to use. And this should open a browser, which allows you to get a token and then log on via Elixir. And then we should be back to our RStudio window. Should have successfully logged onto all of the servers, and we should have assigned all of the tables. And if we use ds.summary, we can see what we've got. What we should have is 4 cohorts: ALSPAC, BCG, BIB, and ProBit. We should have a data frame for each of these cohorts with these 7 variables here. Just checking the messages whilst we're talking. What were you saying, Sido? Could I get an idea whether everybody's got to this stage, or if anybody's having problems and they haven't been able to get to this stage and see the summary of this data? Could you let me know now? It's so funny doing these webinars. You've just got no idea whether you're just like talking out into the ether. I'm
For me,
presuming that people are
I-
listening and
I did manage to do it yesterday, but not today. I do get the
Okay.
device login, successfully connected device, but then I'm not actually being logged in.
so what, are you getting an error message at this point?
So when I clicked on the orange button to log in, I got the lifecycle device login, successfully connected device, and then it stopped.
Okay, and what happens if you come back to your RStudio?
It says the 0% logging into the collaborating servers. I don't know
It
if
says-
anyone else has this.
But it hasn't logged in, did you say?
No.
And if you do dssummary.data,
It's not like
okay,
it
so
is. Yeah.
it's working?
Yeah.
Nice. Okay. So we're logged into the Datashield environment, and we've got we've assigned our data, which means we can now access this data from these 4 cohorts. So before we want to fit any models at all, we want to have a look and see what our data looks like. So we can make a simple scatter plot with age on the x-axis and weight on the y-axis. Okay, so here we go. We've got a scatter plot for 4 different cohorts. And I'm interested what people's initial thoughts about the data is. What jumps out at you looking at the distribution for these 4 cohorts? Thanks, Alex. Yeah, if you feel more comfortable talking in the chat than talking out over the whole thing, then jump in the chat. Yeah, so the variability increases as we get older. A lot of sort of quite a tight distribution at early ages, and then it gets very wider as we get older. Yeah, definitely. What about the shape? I think what I'm interested in is whether this looks linear to you, like there's a linear change in weight over time, or whether it looks more like a non-linear pattern. Yeah, I would agree with this. To me, it looks like you've got this quite steep start, and then it levels off, and then we're going to go up again. Yeah, exactly. I'm just reading the chat here. Thanks, Richard. Yeah, you've got different intervals, so you have to sort of pay attention to the x-axis, but actually BCG is only going up to the age of 5 here. So you're just catching that first acceleration and then leveling off, whereas Probert and Ausbach are going right up to age 20. This is one way to visualize the data. Now, another way we can visualize the data is to split our age into yearly intervals. So essentially binning age into yearly intervals and then plotting the mean weight at each age. If you come back to this and read Rachel's paper, you'll see that there's a figure that she produced, which I'm essentially reproducing here. So we can use a function. So now this is a function from the package DS Helper that me and Cedo have written. And the point of it basically is to make things easier in Datashield that would be a bit time consuming or cumbersome. So this function mean by age allows you to specify your outcome, which is going to be weight, specify your age variable, which is going to be age, and it will split your age variable into yearly intervals and produce the mean of your outcome variable at each interval. I can show you. So what we've got here is a very simple table, 3 columns, the cohort, the age, and the mean. So you can see that what was in long format, I should have probably said that. So our data here is all in long format, but we've split it up here. So we've got the mean at different ages. So the mean for Ausbach, mean weight at age 0, age 1, age 2, age 3. And we've got this for all the cohorts. Now, I think something to emphasize about Datashield is once you get values like this locally, so this is just stored on your local R, you can do whatever you want in R to plot them. So you're not then you need to use Datashield functions. You can use normal R functions because you've got the descriptive statistics back. So for example, I like to use Ggplot, and we can use Ggplot to plot the weight against each year of age. And here's what you get. So you've just got a line graph with these mean values joined up. And you can see, I think, the same pattern from the scatter plot. You've got this initial sort of linear increase, got this sort of tailing off or slowing down around age 3, 4, and then we're increasing again before tailing off into the 20s. So this is how to visualize the outcome, which in this case is weight. We also want to describe our exposure. So we're going to look at how these weight trajectories differ by sex. Now, Datashield, the main functions for getting descriptive statistics are DS summary and ds.table, which work fine. But again, I've written a function called getStats, which calls these functions, but gives you the output in a format which I think is a little bit easier to use. And the arguments to getStats are just your data frame, which is data, the variable that you want to summarize, and then the connections that you want to use. So here we want to use all 4 cohorts. And again, what you've got is here is a list of tables, categorical variables and continuous variables. We only wanted to summarize sex. So for all cohorts, we've got counts for males, counts for females, information about missingness, how many total observations there are for each cohort, how many valid observations. In this simulated data, we don't have any missings. And you can see, as expected, you've got a reasonably even split between males and females in the sample. Possibly more, yeah, there's skew towards more males in the sample. Now, the last bit of information that it can be useful to have with trajectory analysis that you might want to report in a paper is things like how many observations do you have, how many participants do you have, what are the minimum and maximum age of your participants, how many observations did each individual contribute. Again, there's a DS helper function I've written to get this information called getRmStats. And you give it your outcome, your ID variable corresponding to each subject, and your age variable. Takes a bit of time. But what we get at the end is a table here with each cohort and also the combined estimates and some of this information which is really useful to have. So if we take Ausbach, for example, we can see that the minimum age is 0 and the maximum age is about 16. And as a side note, these aren't the true minimum and maximums because it's not possible to get these in Datashield because they could potentially be disclosive. So the minimum is actually the 5th percentile of age and the maximum is the 95th percentile of age. You can see how many total observations we have in that cohort, which is about 130,000. We can also see how many participants we have, which is about 14,000. And then these last variables give us information about the number of measurements that each individual is contributing. So this could possibly name it better, but nMeasurMed is 9. So we can see that Ausbach, the median number of measurements is 9 per individual. Okay, I'm just going to pause here. Cedar, you mentioned people are getting a 403 error.
I'm tracking the server logs and people have trouble to actually authenticate. Well, that's the first part. And then the second part is the authorization. People are also having trouble to authorize. So if people are having those kind of trouble, I can help them in the breakout room. Maybe that's a good idea. But they need to let me know because otherwise I will be alone in the breakout room. So.
Okay, I think I can try and re-invite everybody. Let me try and do this now. Maybe I close it and I start again. Okay. Hopefully, are people seeing an invitation to the breakout room? Alex, are you seeing the invite to the breakout room? I can't hear you.
That's muted. No, I'm not seeing an invite, but I don't know if that's just because I'm now a co-host. But I can
Would
see
anybody else-
the room one is open, so it should be available if you click that 4 buttons at the bottom, the breakout rooms button.
Okay, great. There's an option to join, and you saw the invite. Perfect. So I think what I want to do here, people are having technical problems. If they could go into the breakout room and Cedo can try and sort them out. And I think we will try and push on in the main room, just because we don't want to get too bogged down in trying to solve technical problems. But maybe that's a good point to pause. So this was the first section, which was to visualize the data and get some of the key descriptive info that you need. Does anyone have any questions or comments? Was there anything that was very unclear? You can say in the chat if you'd rather not say out loud. It would be nice to just get some idea of whether this made sense. I'm not sure of the level of familiarity of Datashield of everybody here. Give me some feedback. All right, thanks, Tiffany. I think one of the problems with doing these sorts of tutorials, right, is you've got a nice R script and you can press play and everyone can press play, but maybe as we're going along, it's not always super clear to take in everything and to take in what we're doing. I always find when I go to R tutorials or Datashield tutorials, I mean, I'm not saying they're not helpful. I'm not criticizing Datashield tutorials or my own tutorial, but I do find that you're not necessarily going to come out of the tutorial being an expert in these things. I find that I learn by doing it myself. So when I get to do my own analysis and I want to use a certain approach, that's when I find that I really learn how to do it. But as I said, this tutorial is going to be, we'll keep it available. I'm going to keep the simulated data available. So when it comes to doing your own analyses, hopefully you can come back to this and use it as a template. So, okay, nice. We've had about 45 minutes. What I want to do is go through part 2, which is to fit a simple linear trajectory. Then we can have a break, and then we can come back and move on to some more complex models. So a quirk of Datashield, before we can fit these models, we need to make sure that our ID variable is an integer. And if it doesn't, then everything's going to break. So we can use the Datashield function ds as integer just to convert our ID variable into an integer version of the variable. And the way Datashield works is when you create a new variable, it doesn't create it as a column in your main data frame. It creates it as a separate vector. So to get everything back together, we just have to join this vector we've created, so ID int, back to our data. So we can just look at the col names and you can see now that we've just got one extra variable called ID int, which is just our ID variable, but an integer version. So we're going to try and fit our first mixed effects model now. And we're going to fit a model with four terms: an intercept, age, sex, and the interaction between age and sex. So this allows males and females to have a different trajectory. And these terms are our fixed effects, as I described before. And these are the first half of the formula that you're going to see below. Go down here. So this is the formula we're going to fit here. So weight is our outcome. We have an intercept, which is represented by 1. We have 3 fixed effects, which are age, sex, and the interaction between age and sex. So all of this bit here is a regression model, which should be very, very familiar. All we're adding at the end is the bit which gives it the name mixed effects, which is some information about clustering. And what this syntax is saying is that our clusters are defined by ID. So we're saying that each individual is a separate cluster. And that for each cluster, we're going to estimate a different intercept, which is 1. So we're going to allow each individual to have a different intercept. So we're going to estimate fixed effects for the whole sample, and we're going to estimate a random effective intercept. Now, this bit here can get a lot more complicated. You could have 2 or 3 levels of clustering. You could have random slope models as well as random intercept models. But the Datashield LMER SLMA function is just a port of the, I think it's the LME function in base R. So any complexity of model that you can specify in base R, you should be able to specify in Datashield. So we're going to fit the simplest one here. For people that are more advanced in multi-level modeling, you can specify more complex data structures here. I've explained some of this in the text. I'm not going to read through all of it, but you can come back to it if you want to go through this again. And just to go over this function here, this is LMER SLMA. So this fits mixed effects models for each cohort, and then it just pulls the fixed effects by meta-analysis. So we can run the model now. Okay. We're getting an error. People familiar in Datashield, I feel like I see this line here. There's some Datashield errors listed with Datashield.errors in my sleep. I'm not sure why this has happened. It could be that the load on the server is too high. Let me try again and see how we get on.
Have you tried doing Datashield.errors?
Yep, it said execution failed, eval failed.
Ah,
I'm not sure if Sido can hear me or if he's just in the other group.
CEDA is in the other group, yeah.
Okay, it's worked for Anna, nice. And Lucinda doesn't have the error either. Okay, maybe everybody else is allowing it to work, but it's not for me. Okay. I'm going to try and log in again from the start and just get up to these steps quickly and see if that fixes the problem. But I'm glad it's working for everybody else. Okay, so it seems to have logged in again. I need to just go over this step of making my integer variable. And let's see if I can fit this model. I'm sure Dimitri's around and has got any ideas as to why I'm getting this error.
Now it's a different study. I think it's something with the server. Can we add Sido back to this room?
Yeah, let me try and call him back. CD, are you back with us? I think Alex has gone to fetch him. Cedo, are you back with this?
Yeah, but I did. Sorry, Alex. Yes, I'm back.
Do you have any idea why? So other people are able to run this step, but I'm getting a error message. We think it maybe is too much load on the server.
Yeah, that looks like it. Yeah, it's too much load, and you've lost your session. That's a bit of a problem.
Okay, shall I log in again?
Yeah, you need to redo the stuff that you did.
That's
And
fine.
I'm now increasing. That's a good. I was. It's already. It's already a very big server, but still it needs to be a larger server even more. So that's okay.
Thanks, Cedo. How are people getting on in the other room? Are people still struggling with some technical issues?
Yeah, there was some login issues, and there were some authorization stuff that wasn't correct.
And are people sorted, or do you need to go back and help them?
I need to go back and help them.
Okay, can you just hold on here and see if I can get this model to fit before you go back?
Yeah, sure.
Nice. Okay, you're released. You can go and help people.
Thank you.
Great. So we have fitted our first mixed effects model, which is a very simple one. And we've got the output here. So the output's quite long. You get this big list of different things that might be helpful. We can have a look at what we've got. So this here is giving us the fixed effects. So again, this is the bit that would be exactly the same as if you'd run a normal regression model. For each of your 4 studies, you've got coefficients for the intercept, age, sex, and age times sex. This bit here gives us the meta-analyzed coefficients. So this is pool by maximum likelihood. It's the meta-analysis of these coefficients in each cohort. And here we've got information about the random effects. Was that a comment or question? Okay. Now again, all the information you need is here, but what we find is that it comes in a kind of nested list, and it can be a little bit tricky to manipulate and use this information that is just outputted raw by Datashield. So again, there's a function that I've written called lmtab, and all this does is it takes a Datashield model. So here, the model we've saved our model as model1.fit, and it extracts all of these bits, but it just puts them in a slightly neater format, which is a bit easier to manipulate and use. So you specify the model, the type of model, which here is LMER. You give it the names of the cohorts. You have an option to say whether you want the confidence intervals separate or pasted together, which can be useful for tables, and the direction that you want your table. Okay. So we've got a new object here called model1.coef. And here we can look at the fixed and random effects from the model. So the fixed effects now we've got it in one table for each cohort, for each variable, the estimate and confidence intervals. Having it in this format is kind of useful because we can then manipulate it more easily. For example, if we want to look at the fixed effects separately in each cohort, we can use some tidyverse syntax here to group this table by cohort, and then to split the grouped table into separate groups. So here you've got your coefficients for each cohort separately. Or we can take this table of coefficients and we could just filter it. So we just showed the combined coefficients, so the meta-analyzed coefficients. So that will be given here. Using these sort of functions isn't a tool, these DS helper functions isn't compulsory at all. You could do it entirely just from the raw Datashield output. I just like things to be neat, which is why I use them. So we can also view the random effects here. Now we can't view the individual random effects, so we can't view how each individual differs from the intercept, because this could potentially be disclosive. But what we can get is we can get the standard deviation of the random effects. So this is shown down the bottom here. So for example, for Ausbach, you can see the standard deviation of the random effects for intercept 3.84. Go back up and look at what the average intercept was for Ausbach, it was 3.87. So this is showing that there's actually quite a lot of deviation between individuals about what the intercept is, so what the starting weight is. We can also view the residual error, which is the bit left over. And you can get this here. So this is the standard deviation of the difference between each individual line or trajectory and their observed data points. Whereas this is the difference between the standard deviation of the difference between the mean intercept and each individual intercept. Actually, maybe I'll come back to this point. I'm just going to reshare my PowerPoint slides to try and make that bit clear, because I think it's useful to know. Can everybody see my PowerPoint slide again? Someone nod? Yeah, Dimitri's nodding. Okay, thank you. So essentially what we've got in a mixed effects model is we've got two error terms. So this is our normal error term E, and this is the difference between each individual person's trajectory and their observations. But we also have a second error term now, which is U, which is the difference between each individual's intercept and the mean intercept of the whole sample. So we've split our error into two bits, E and U, and the standard deviation of both of these error terms can be returned by Datashield. Okay. Come back to R. Okay. And with trajectory analysis, the whole point or exciting part is that you get a nice graph. So this is the steps now that we need to go to turn these coefficients, which we've shown here, which are the intercept, the slope, the interaction between the slope and sex, and then sex, into some plots. And there's quite a few steps we need to go to do this. So I'm going to go through these steps, then we're going to have a break, then we're going to come back and fit some slightly more complicated models. So what we want to do is we want to get predicted values based on our model at different values of the variables in our model. So we want to predict weights at different values of age, different values of sex, and then different values for the interaction term, which is age times sex. So what we have to do is we have to make a reference table which has all of the values of our variables that we want to get predicted values of weight for. Just going to check the chat.
Sorry.
Sido's just saying, no, that's okay, Sido. So we're going to make a reference table for males, which I will do. A reference table for females. And then we're going to join them together. And if I show you what we've made here, we've simply made a table with 3 columns, which are corresponding to the predictor variables in our model. So we've got values of age from 0 to 25. We've got values for our interaction term between age and sex, and we've got values for sex, which here is 0. But you can see we've got 469 more rows. So if we went further down, you'd see that we'd have different values for age and different values of sex. So we want to get predicted values for age from 0 to 25, and then both for males and for females. And this is a similar process that you would use if you used the predict function in R. You would feed it a data frame of the values of your predictor variables at which you want to get your predicted outcome at. You can then use another DS helper function called predict LMER, which takes your model with the coefficients. It takes the data which you want to get predicted values based on your model at, and then it outputs it for you. I'll call this plot data. So we've got a table here of the cohort, the variables in your model, intercept, age times sex, and sex. You've got the predicted value. You've got standard error, low confidence intervals, and upper confidence intervals. So we've almost got everything we need. Well, we do have everything we need now to plot our trajectories. Now, one thing which is maybe a bit fiddly, but here we've got, for all cohorts, we've got predicted data from ages 0 to 25. But if we go back to our scatter plot, if I can load it, not all cohorts actually have data up to this age. So for example, BCG's only got data age up to 5. So we might not want to predict plot a trajectory for BCG all the way up to 25 because it doesn't have data there. So we can use this function called trim pred data, which just trims the predicted data we've generated at the actual upper and lower bounds of the age for that cohort. So for min, you just provide a vector of the lower ages for each cohort, and for max, you provide a vector of the upper ages for each cohort. The vector's 5 thingies long because we're also providing the upper and lower ages for our combined trajectory. So we've just trimmed our predicted values. We want to make, here we're just going to set sex as a factor. So this just means that we can give it labels of male and female rather than 0 and 1s, which should make our plot a bit clearer. So we're getting there. So we have our predicted data for males and females, and we've tidied it up a little bit. Now, the other thing that would be nice to do is to overlay our predicted trajectories with our observed values. So here we've got the observed, these are pseudo observed values for each person in each cohort. Now, Dimitri wrote some really nice functions and has a very nice paper on it, which basically takes the observed data and applies a formula. Dimitri, do you want to tell us how you pseudo-anonymize or how you anonymize the data? Because it's very neat.
Yeah, basically you apply anonymization techniques on the real data and you display the anonymized values. And there are 2 main techniques that we use. One is probabilistic anonymization. So for example, if you want to create a scatter plot and you have 2 dimensions, you add a random noise in each variable separately. And this random noise has some specific characteristics based on the real variability of the actual variables. This is one technique. And the other technique is deterministic anonymization, where we use a type of not machine learning, it's a type of k-nearest neighbors algorithm, where for each data point that is displayed here, we search for the k-nearest neighbors, and this k can be specified by the analyst. And we then, when we identify each cluster of k-nearest neighbors, we estimate the centroid and replace each real point with this centroid. Yeah, but there are more details for the procedures, and maybe it's, if you are interested, we can share this paper. Or
this is super useful because what it means is you have something which is pretty close to the original data but is anonymized. So this is really nice because then you can use this in plots.
Yeah, basically using these techniques, we are trying to protect the privacy but also we want to keep the statistical properties that are displayed stable. So what you see here, they have similar properties with the real data.
Thanks, Dimitri. So what the last step now before we plot our first trajectory is we want to get the values that are all of these points here in the scatter plots. And again, there's a simple DSL function called getAnonPlotData, which simply, rather than returning the plots like this, it returns a table of all of the values in the plots. And the advantage of doing that is it means that you can then build more complex plots just on your own R server. If you want to, for example, like we want to combine trajectories with observed data. We've got some more Datashield errors. It may be that I've spent too long talking, or it could be that
Session
loading.
gone again. Session is gone again.
All right.
Oh, God.
The server's taking quite a hit, Sido.
Yeah, I wasn't expecting this because that means that a lot of people are able to do it. That's the nice thing.
Okay, nice. So hopefully some people are getting through. If it's me that's the one that's struggling. So I need to catch up. So every time this breaks, then I need to rerun some bits.
I can increase. I don't know if it's.
Okay, yeah, a few people are getting this error.
Just a sec. I will increase the memory again, but then from each node.
Should we try again, Sido, or are you still sorting things?
I'm trying to sort things in just a moment. Here we go. Okay, again.
Okay, so for people who've been booted out, you're going to have to go through this first step here of logging on again. And you don't have to run every single step, but the step that you do need to run is starting from line 252. So converting the ID variable to an integer. And then running your model. And then getting your predicted values. This is what broke it before. Let's see if how we get on this time. Okay, nice. It's worked for me. So what I've got here is a huge table of about 800,000 values, and these are the age and weight for each of the participants in our samples, but they're anonymized. So they're not the actual age and weight, but they're age and weight, which, as Dimitri said, maintains the statistical properties. Okay, so quite a few steps, but we are now at the point where we can plot these trajectories. Now, for people who know Ggplot, what we're doing here is we're just building up different elements of our plot. We're going to plot the observed or the pseudo-observed values as points. And we use the function sample_frac to just take a 1% or 0.1% sample of the observed values, so we don't overwhelm our plot. We use geom_line to get the predicted trajectory, the predicted values. We use geom_ribbon to plot the confidence intervals. And then we add a few other bits. So we add the limits of our X and Y axes. We add a few labels, and then we label our sex trajectories. Here's what you've got. You've got a simple linear trajectory for males and females. You've got some idea of the observed data, which is the dots. And this is for the meta-analyzed trajectory, so the four cohorts. And we can also plot the trajectories for each cohort separately. So all we're doing here is we're adding this line here on 505 called facet wrap, which is basically saying we want to split this up and we want to plot it separately for each cohort. And we want to exclude the combined plot for now. So if you do this here, then you can see the plots by cohort. So you've got the observed data and then your predicted lines. Now I've put the question here of how well you think the model fits the data. I'd be interested, maybe it's obvious. For me, the fit doesn't look great, but I'd be interested to hear what other people's thoughts are. Yeah, thanks, Serena. I would agree. I'd agree with this. I mean, we've just plowed straight through the middle of some quite interesting non-linear change here with a straight line. So this is a trajectory, but it's not a very good trajectory, and it's not one that that fits the data particularly well at all. Yeah, thanks, Cedar. That's a good question. Could I get some indication of who's with me and whether we've lost anybody? Okay, nice. Marika and Tiffany are to the plots. Nice, Gemma too. Okay, great. Okay, and Priya's getting an error. Priyanka's getting an error. Should we just take I was planning to have a longer break, but I think we've been a little bit slowed down by some technical problems. Should we just take 3 or 4 minutes if anybody just wants to pop to the toilet or get a drink or stretch their legs, and then we can come back and push on with the next part of the tutorial. And maybe if anyone's having problems still, Sido could keep trying to help them out with this. And then we're back in 2 minutes. Okay, I think I'm gonna try and push on with this so we can get through most of it in the next half an hour. I can see Dimitri and Alex, so I'm not sure who else is here. Someone say hi in the chat if people are still here or whether people are still on a break. Thanks, Annemiek. Okay, nice, good. We're all here, great. Right, so what was wrong with this approach? Well, the problem really is we didn't allow for any nonlinear change. We only allowed weight to change linearly as age changed. So what you get is a straight line. And actually, most growth or change, natural growth or change, doesn't follow a linear pattern, as we can see here. So we fit a basic model, but it's not a very good one. So one way to try and improve the model is, rather than modeling weight as a function of age, we model it as a transformation of age. So for a starting point, we could try and model weight as a function of age squared rather than age, and see if this gives a better fit with the data. So the first thing that we need to do is we need to create a new variable, which is our age variable to the power of 2. So we need to square our age variable, which we do here. And then we join it back in with our original data. And again, we can check whether this has worked. And here we go down the bottom, we can see we've got a new variable age underscore 2, which is just age squared. Now I'm going to go to this bit relatively quickly, because all we're doing here is we're doing the same steps that we did before, but rather than using age as one of our fixed effects, we're using age squared. So it's exactly the same model as above, but with age squared rather than age. So we see if we can get the model to run without the server breaking. Nice. And then all of these steps here are the same steps that we did before. So we need to create a reference table of the predicted values that we want to get of weight from our model. I think one thing to note here is that we, in our predicted values, we've got reference values of age, but we also need to create corresponding values of age squared. So because we want to be predicting weight at these values of age squared. And then we can go back from this and plot our actual graph against age. And here we're just following the same steps as before. We're going to get predicted values at these values of age squared, the interaction and sex. We're going to trim our predicted values so they only predict at the between the age ranges of which we actually have data. And then we're going to set sex as a factor to make our plots nicer. And then we can plot this revised model with age squared rather than age. Okay. Thoughts on how good a model that is and whether it's an improvement or not? Yeah, thanks. I mean, it's a slightly obvious question, but yeah, linear. Yeah, you're probably right. Actually, we probably have got worse by this. I mean, we're trying at least, right? Which we're allowing for some non-linearity in our trajectory, but I think actually you're right, Dimitri. It is, and Richard, I think it is worse than just a simple linear trajectory. So we can do better than this. Now, what I'm going to finish with is showing how to use a fractional polynomial approach to trajectory analysis using Datashield. So what we've used is one transformation of age, but what you can do is use more than one transformation of age. So you have two age terms in your model, which are different powers of the original age. And this is called the fractional polynomial approach, powers that involve fractions. Now, you don't just have to use 2 age terms. You could use 3, 4, 5, 6 age terms. The more age terms you include in your model, the transformations, the more complex nonlinear change you can capture. Problem is, the more you use, the more chance you have of overfitting your model. So again, I'm following some nice papers by Kate Tilling and Laura Howe and Deborah Lawler from Bristol, where they show, or they suggest using these 2 transformations of age. And their suggested approach is that we take 7 or 8 different transformations of age, and we try lots and lots of different combinations of those age terms, and we see which fits well. So we might include a model that has age and age squared. We might include a model that has age squared and age to the power of 0.5. And we do different combinations of these transformations of age, and this allows our trajectory to vary in different ways. And we fit lots of these different models, and we see what actually gives the best fit. And then we can use that to make our final trajectory. So I'm going to talk through, we might get to this in 20 minutes. I'm going to talk through how to do this in Datashield. So the first thing we need to do is we need to add a very small value onto age. And the reason we do this is because if we start trying to produce powers of age, if we have values of age which are 0, then we're going to get infinite values and we're going to break our model. So we need to make sure that there are no values of age which are 0. So we're just going to add on 0.01 to age to start with. We're then going to remove the original age column from our data frame, and we're going to join our new one back, which is just age with a very small amount added. Okay. I'm going to try and log back in again because it looks like we've reached our server limit. Some of you, actually, if you could let me know if people have been able to run that step, that'd be nice.
Tim, just a sec. I will increase it even more. So before we connect, lots of people that are experiencing problems.
Okay. Why didn't you increase it this much the first time, Sudo?
Because I'm taking over my complete cluster, which is also servicing other applications.
Okay, that's a good answer.
So I need to do it in steps. Hopefully it is. Just a sec. This is now 2.5. So you need to specify which steps they need to rerun. So I think the login block, and then
I'm just considering, Sudo, the last bit is the most resource intensive thing, and I wonder if everybody runs it, whether it might blow everything up.
yeah, that's true. So maybe you run it first, and then the other people can run it after that. It's also
Yeah, I think that might be a good idea. So if I could ask, just from now on, if people just watch what I'm running and don't try and run it themselves, I just don't want to blow up Sudo's server. And it'd be quite nice just to be able to show you what the steps are.
Yeah.
And then once I've got it working, then then you feel free to run it yourself.
Exactly. Okay, it's up again.
Okay, nice. So I'm just going to go through the key steps that I need to do. So I've logged back in. I need to create the integer version of the ID variable. Okay. I need to get our observed data because we're going to use that in a plot in a little bit. Now, this actually is a good example of how not to do things well in Datashield. That what I should have done, and I forgot to do, is to periodically you can save the workspace at the point at which you've got to, which means that if it crashes and you need to reload it, you can go back to a saved point. I'm not sure, I can't remember the command. Maybe Dimitri or Alex could just put the command in the chat just for people's reference of how to save your progress within a Datashield session. That would be super nice. Okay, so we're back here. We're going to try and fit some fractional polynomial models using multiple transformations of age. So we're going to add a little bit onto our age term to get rid of any zeros. And then we're going to join this new version back on. And again, if I could ask people just to watch for this point, that would be super nice. So next thing we want to do is we want to create lots of different transformations of age. So you've got age to the power of -2, -1, -0.5, log of age to the power of 0.5, age squared, and age to the power of 3, age cubed. Now you could do all of this manually. So if we go back up to here, we created a version of age by squaring age, joining it back into our data frame. But this is a bit tedious. So I've written a function that does it for you. You can tell it every single transformation of age you want, and then just a label for these different transformations. And it will transform your age term by these powers and join them back into the data frame. Okay, so we get a message here saying that it's created these transformations. We can get a summary using getStats of the transformations that we've created. You can see why I've asked you to hold off here, because it's quite resource intensive, these bits, and it's going to break if we all try and do it. But you can see here what we've done. So for each cohort, we've got this transformation of age. So we've got age to the power of -0.5, we've got age squared, which is a big value, we've got age cubed, which is an even bigger value. So we've got a data set full of transformations of our age term. So now we want to try to fit different combinations of all of these. And in fact, there's 28 different combinations of these age terms. And again, we could do what we've done up here, for example, or where are we? Second model. Here we go. We could write this out 28 times, just specifying different different combinations of age terms. But again, I've just written a function that should make this a little bit easier. It's called make LME R form, and it just makes a load of formula containing different combinations of these age terms. We can have a look at it here. And this should make it clear what we're doing. So these are lots of different models that we're now going to fit. We've got a model with two age terms, age and age to the power of -2, age to the power of -1, and it goes down. This is just the top 10 of these, but we're going to fit every combination of paired polynomials and see which one fits the data the best. Is there a need to center x minus mean to avoid large values and floating point problems? Carol, yeah, possibly. Would do you want to say a bit more? I realize you sent me this in the direct message. I'm putting you on the spot, but could you say a bit more what you were thinking here?
Sorry, was that a question to me?
Yeah. I was just wondering if you
yeah.
could just share your question.
Well,
just for
I
everyone.
remember from basic statistic that if you have very large numbers, and then you can run into troubles with estimations, and the solution to that is to centralize the by distracting the mean from the original values. Is that needed, or is that this program resilient for those problems?
I don't know, Dimitri, could you comment?
Yeah, some people, they centralize the variables, the explanatory variables, but I haven't tried to do exponents of this type of transformations to see if there are any problems.
Okay.
But if you centralize the variables, or if you standardize those, you will get similar conclusions at the end. So it's a good practice in general.
Okay, thank you.
I've got a question from Serena. Yeah, thanks for asking this this question, Serena. So what we're doing is we are fitting the models for each cohort separately, but then we're combining the estimates by two-stage meta-analysis. So this isn't, I should have probably made this clear at the start, this isn't the sort of full one-stage virtual pooling approach where you fit on the data as if it was one data set. You're fitting 4 separate models here, and then you're meta-analyzing the coefficients. If that clears it up. No, I don't apologize. I need to make it clear. Oh, Carol, would you mind muting? Or someone needs to mute. That's a good question. If centralizing, will it centralize in each study separately? Will it then cause trouble when meta-analyzing? Yeah, I guess you'd need to centralize the same in each study to avoid those problems.
Can I say something, Tim, about
Sure.
that?
Yeah, please.
I'm expecting that when you centralize according to the study-specific mean, actually the slope is the same as without centralizing. Only you can interpret more easily the intercept, and yeah, there is less variability. But I suppose that it doesn't cause any trouble with meta-analysis.
Okay, thanks, Daniela. Great. So what we're going to do now, and this step's going to take a few minutes, so if people have more questions, we can talk about them whilst this is running, is we're going to fit all of these models. So we're going to fit 28 models with different combinations of these age terms. And this is why I've asked people not to run it, because I think if 30 people try and fit 28 models, it's not going to work.
It dies terribly, yes.
But you can see as it's running, it's just fitting all of these models in turn. You can see the different combination of age terms that's being fit, which would allow different shapes of the trajectory. And it will just take a couple of minutes. So if anyone has any questions or anything they want to put in the chat for now, we can talk about it whilst this is just finishing off.
Just to clarify what you're actually doing here now. So
sure.
If people are worrying about server capacity, Tim is now trying to fit the model on 4 cohorts which rely on the same server. So it's usually you fit the model on 1 cohort on 1 server. So in real life, you will do this spread over the server environments, which allows you to do this maybe simultaneously as well on 1 cohort instead of 4. So the server issues that we're having right now are not actually how do you say it? Comparable with what you're going to experience in the actual analyses.
Okay, so we've got a message here that not all models have converged for all cohorts. And we can look at the output and get some information here about what models have not converged. So there may be some convergence problems in some cohorts for these models here. I'm not going to go into this in detail now. Now, there was a question in there. Okay, so there's two questions here. Using two age terms in the same model won't cause multicollinearity. And would it make sense to put all terms in or use stepwise regression forward, backwards? Now, the first question, we may be getting to the limit of my stats knowledge because I'm not a statistician. Daniela's here.
Yeah, I can say something about that, but here is different because, yeah, obviously the same variable, but you want to model the pattern of that variable. Then actually you don't interpret the estimate for age and, for example, the cubic age. You interpret the pattern given by the two terms, the two age terms. Then is the only way to do it, to include them in the same model. And I repeat, you interpret the pattern, not the singular estimate of each term of age, actually.
Thanks, Daniela. That's a really nice reply.
And yeah, you can say also about stepwise. I don't know if in Datashield it's possible or not Tim, if you want to answer from the datasheet point of view.
Yeah, I'm not sure it is possible. I think Dimitri might have to answer this one.
Sorry, Tim, I missed the question.
If you can use stepwise regression to select the variable to include.
Yeah, no, it's not. We don't have a functionality for that.
Yeah. And however, it would be a little bit a problem with meta-analysis, because I suppose that in different cohorts, also the final model would be different. So you could not meta-analyze combine the results, actually.
Can I just I say something about the piecewise, the stepwise. Basically, we have a type of regression which we use for survival analysis, where we use the piecewise exponential regression. I'm not sure if that, but in that way we need to put the data in a specific format, and we have a function which is called dslexis, which does this, but I'm not sure if that is only specifically for survival analysis, or if we can use the same technique for any type of stepwise regression. Yeah, I don't know the final answer. So my son is up. So sorry.
No problem. Thanks, Dimitri. Okay, so we're almost at 2. I think I've probably got another 10 minutes to go. So I'm going to go to the end, but if people need to leave at 2, that's absolutely fine. So what I'm going to show you here is the output from what we've just done. So we've got all of these different models, different combination of age terms that we've got, and we've got the negative log likelihood for each study, which is an indicator of how well the model fits. And then we've got the summed negative log likelihood across all studies. Now, the reason I've done this, or the reason we could do this is, so the point Daniela was alluded to, is if we want to fit if we want to make a combined trajectory or a meta-analyzed trajectory, we need to, across cohorts, we need to have the same model in each cohorts. So the idea of this is to fit all models. We can see which fits best in each cohort, but then we can see which model fits the best across all cohorts. And here we can see that the best model that fits across all cohorts has 2 powers, h to the power of 0.5 and age squared. Now, in Rachel's paper, which I referenced in the slides, she takes probably a better approach and a more thorough approach, which is to fit all of these models on a part of the sample, and then to test the fit on another part of the sample. Now, that's possible in Datashield. I've just done a slightly more simplified approach here. So just looking at this empirically, this is suggesting that the best fitting model would have these two powers, h to the power of 0.5 and age squared. And then we can just fit this model manually here with these two age terms. So we've got age to the 0.5 age squared, sex, and any interaction between sex and these terms. And then to make the plots, again, I'm just going to skip this, but we're doing the same procedure as we did before. We're creating some reference data to get predicted values at here. We're going to get the predicted values from this model. We're going to trim these predicted values to fit the actual ranges of the cohort, and then we're just going to make our data a little bit neater for plotting. And then we make the same plots. We're just plotting our age against our predicted values of weight. And with this set of terms, it looks to me at least like we've made some progress. So we're definitely capturing this initial acceleration and slowing here. And then we're capturing this re-acceleration around this age here. We can also look at the, so again, just to come back to Serena's point, so this is the meta-analyzed, this is the meta-analyzed, I was just reading Serena's comment, it's cute fit, yeah. This is a meta-analyzed trajectory, so this is the coefficients of all four cohorts meta-analyzed. And we can also look at the trajectories by each cohort here. So again, we're just using this facet wrap argument. And you can see, again, for Ausbach and Probit, it's a pretty good fit. And with BIB and BCG, you're capturing this first part of the trajectory. So we've captured the initial growth, followed by reduction in growth rate, and then followed by an increase into adolescence. Now, this model still isn't perfect. What problems can you see looking at the graph? Are there things that worry you about these trajectories? Well, I guess what worries me is that it's getting a bit out of control at the end. I mean, if we carried on at this trajectory, you know, for another 10 years, the predicted weight is going to be huge. So I think one of the problems of these fractional polynomial models is they become less accurate at the extremes. Also, you could argue that if we had more data and we got up to 25 and you had the slowing off of weight that you'd expect, then you would get different coefficients and they would fit the model a bit better. Okay, so for me, this feels like some really nice progress. We've managed to fit a non-linear model that fits the data pretty well. Now, we've done this for weight, but of course, you could do this, whatever your outcome. You could do this for height, you could do this for BMI, you could do this for blood pressure, you could do this for a mental health outcome, whatever your outcome is. Or if you want to look at a different exposure, if you wanted to do this, say, looking at differences by socioeconomic position or any exposure, all of the steps that we've done so far should be able to recreate with different outcomes and different exposures. Now, the very last thing I'm going to show you before we end is just how to check the fit of this model. Now, here I'm approximating a table in a paper by Kate Tilling that I mentioned earlier. And essentially what I'm trying to do is to show how the predicted line, the predicted trajectory differs from the observed values. And again, we're going to use this function mean by age, and we're going to split our age variable into some periods. So 0 to 1, 1 to 2, 3 to 5, 6 to 10, 11 to 15, 16 to 18. And we're going to get the mean values of weight at these different age categories. Now, this also takes a little bit of time to run. And the reason this takes a bit of time to run is because essentially we're creating different subsets of the data between the different age periods. We're then getting the mean values in these subsets, and then we're putting it all together into a nice table. But the reason this is important is because we want to be able to see how closely our predicted values, how closely our model fits the data at different ages. Because it may be that it fits very well, say at early ages, but it starts to fit the data less well at later ages. And it's useful to be able to see this. Okay, so that was a bit time consuming, but what you can see here is for each of the cohort, we've split it into different age periods, and then we've got the mean observed weight at these different age periods. So for Ausbach, the mean weight between ages 0 to 1 is 5.8, etc. Just going to rename one of the columns to observed, so we know that this is our observed values. And now all we're going to do is we're going to get predicted values at exactly the same age band, so they correspond to each other. Here you've got predicted values for Ausbach and the different cohorts between ages 0 to 1, 1 to 2, etc. You can join the observed and predicted values back into one table. And then we can see what we've got. Again, I haven't gone through all of this code, but you can sort of read through it and look at yourself. But what you end up with is a table for each cohort with your observed value, the different age, your predicted value at that age, the difference between your observed and predicted values, and then the limits of the difference based on the standard error of the predicted values. And for Ausbach, the fit's not too bad. It varies at different ages, but sort of randomly across the ages. I think the cohort where it really struggles is Probit. You can see around the 6 to 10 and the 11 to 15 age. The data, the fit isn't that great. You've got quite a big difference between the observed and the fitted values. But if you want to produce a table like this, this is how you go about doing it. Okay, that's all I've got to cover today. Now there's different ways that you can model trajectories and repeated measures data. So one thing that I think we're going to start working on next is implementing spline models in Datashield, whereby you split up your age into different periods and you fit linear or cubic spline models between those different ages. But as of yet, this isn't possible in Datashield. Okay, I've got a question from Serena. I may have missed this. Can you say a few words on how we use these trajectories as outcomes in our papers? Yeah, sure thing. So I guess, so for example, I'm working on a paper looking at how child depression trajectories of child depression relates to maternal socioeconomic position, for example. So I'm interested in seeing at what age do you start seeing differences in child mental health problems between lower and higher socioeconomic positions. So then you can include as a fixed effect in the model, say maternal education as an indicator of socioeconomic position. And then you can start seeing different trajectories for children's mental health problems by socioeconomic position. Or you might want to see how respiratory outcomes are affected by a single exposure in pregnancy. Does that answer your question, or have I not quite got to it?
Yeah, no, I was just wondering if we should use some of the like if you use the trajectory as it is, or if you extract some parameters from the trajectories and you use this as your outcome. Just this. If you, it was more a technical question rather than a, yeah. I mean, I would like to look into air pollution, for example, and growth trajectories, and just to know if you just use the trajectory as your outcome itself, or if you, I don't know, if you take some parameters and that describe the trajectory and use this as outcomes.
Yeah, no, that is a good question. I think the point Daniela made is a good one, that using this fractional polynomial method, actually the coefficients for transformations of age are not particularly interpretable or are not super informative. So what I might do, for example, is to say, look at the difference. If, say, I've got a trajectory and I've got a binary fixed effect, a binary exposure. So say you had like high and low air pollution, if you were going to do it in that respect, and you were predicting growth trajectories stratified by, with a fixed effect, or stratified by high or low air pollution. Then you could look at different ages, what the differences were in your predicted values from your trajectories, based on whether the children were exposed to higher or lower levels of air pollution. So yeah, so that's one thing you can do, is to compare predicted values at different levels of your exposure. Okay, so there's quite a few more questions here. What is a good fit value range? Yeah, I'm not sure I could give you a hard and fast rule on that. I think, again, for questions like this, I would sort of hold my hands up as not being a statistician, and I generally depend quite heavily on other people's papers by these. So I would suggest going and having a look at some of the papers that I referenced in the initial presentation. And there's a few questions about having the link to the script. Yeah, Alex, do you think it would be possible to keep the script somewhere on the Datashield website?
I would suggest Google Drive, but I can link to it from the Datashield website. Yeah.
So maybe we could, I think everybody is signed up for this workshop, so we can email around. We'll work out the best way to store the link to this, and we'll email it around so everybody's got a copy of it. Richard, follow your comment. It's not possible to fit piecewise linear spline models. Am I right in assuming that cubic regression splines would not be possible either? Yeah, at the moment it's not, but this is quite high up on my list of things to do, because I need to do it for some projects. So I'd imagine maybe within a month, I want to develop cubic spline functionality in Datashield. It's less of a Datashield problem, I think, because it's just about finding a way to do the transformations to create the splines. But this will definitely be possible. I don't think this would be conceptually or technically very difficult. Is there some correlation structure between repeated measurements assumed here? I may possibly, could you expand on that? I might ask Daniela to help out with this question.
Yeah, actually, I don't know. It depends on what you have implemented, because it could be identity matrix or a symmetric matrix. Actually, I should know. Have you implemented the basic R command?
Yeah, I think I will have just used the basic R command.
Probably the identity matrix. I should check in R what is the correlation structure they fit.
Thanks, Daniela.
Yeah.
Tim, sorry, it's Gabriella here.
Hi, Gabriella.
Hi. Are these based on the random slope models, right? The multi-level random slope.
This here is just the random intercept model.
Okay, random
So I've
intercept
chosen the
model. Then I
simplest.
think no. I think there's not a correlation structure assumed for the repeated measurements, because that would imply a random slope on top of the random intercept.
Okay, nice. Thanks, Gabriella.
Oh, sorry. And I've also forgot to say, well, to ask actually, do we have these slides for this workshop?
Yeah, I'll try and make everything available. I just need to chat with Alex and Datashield about the best place to put it. But we'll email around with the slides and the RMD script.
Great, thank you. Great work. Thanks.
I'd also just add that when people get to doing these models themselves, if they've got any problems or issues, or they want to go over anything in this script, just drop me an email, or me or Dimitri or Daniela or anyone. Lots of people have been involved in making this workshop, but we're very happy to help people with sort of particular issues or projects. You can find us on Slack or drop us an email, and if we can help you, we will.
You can rerun the analysis at any time. So this is a permanent environment that we're using for these kind of workshops, and you can play around on it as well if you want.
Thanks, Ido, and thanks for all your help getting this running and keeping it on track today.
Well done, Tim.
Yeah. All right. Thanks, everyone. If anyone has any more questions or wants to stay around and chat about anything, I'll hang around for 5 or 10 minutes. But if not, then thanks everyone for joining. I hope that it was useful.
Thanks, Tim. Thanks a lot.
See you guys.